All right, section 2.8 we started last time, and we had talked about Raleigh's theorem and the mean value theorem, and we had done a couple of examples, I believe, or at least one example here at the end. And then theorems 8.2 and 8.3, and that's where we left off, right. So we had talked about 8.2 and 8.3. Let me just kind of remind you 8.2 and 8.3, the idea when we did this example, because I know that when we left last time I had a couple people asking questions. I want to make sure that you understand how this process sort of works. What these theorems tell you is that if you have something that has n solutions, that has like n x intercepts, and it has one fewer than that, has at least one fewer than that places where you have horizontal tangent lines or slopes of 0 or derivatives equal to 0. So when we were looking at this particular one right here, we were trying to find that it had exactly 2 solutions. And so exactly 2 solutions means it cannot have fewer and it cannot have more. So the first thing we wanted to show is that it cannot have fewer by looking at the intermediate value theorem. The intermediate value theorem says that if you're above the x-axis, below the x-axis, above the x-axis, for example, then you had to cross the x-axis twice. So that was why we knew that we don't have fewer. So we don't have fewer than that because we have this above, below, above going on in terms of just flat out x, plugging in x values and getting out y values. And then we want to show that we don't have more. And kind of like what we're doing down here is we're saying, okay, I know I can't have fewer than 2, so let's pretend I had 3. Okay, let's say we had 3, and let's see what would happen. Well, if I had 3 solutions, then what that would mean is that I would actually have to have more solutions up here, and that's where I run into a problem. So what we ended up doing is we ended up finding how many solutions we actually had. So I think I just said that backwards, I apologize. If I had 3 solutions here to the original problem, then I would have to have at least 2 solutions, 1 solution less, for the derivative. Well, the problem is I did the derivative down here, and I found out that the derivative only had 1 solution. Well, if the derivative only had 1 solution, then there's no way I could have had 3 original solutions. 3 original solutions, meaning I crossed the x-axis 3 times, would mean that I have 2 places where the slope's 0, and I simply don't. So that's where we were on that example. All right, we're going to do one more example, and this one is similar to the last several that you had on your homework. I think I told you it was 34 and 35. I think it might have also been 30 and 31. Yeah, that was the one you were looking at, wasn't it? Yeah. Okay, so it's actually the last several, and it talks about whether the function's increasing or decreasing. Or neither. And we're going to talk more about this idea of increasing, decreasing, or neither in Chapter 3 as well. But here's the idea. You know some of the pieces of information about this, so let's actually talk about what you know about increasing and decreasing. So let's talk about what happens when we have a derivative that is positive. This actually came back. This is a good piece to be thinking about reviewing from Section 1, 2.1. Do you remember what we did in 2.1 with graphs? You were given a graph, and you had to draw a graph of its slope. Maybe it was 2.2. Do you remember doing that? Well, this is kind of where that came from. Remember, one of the things we did is I had you write down all these details about where the graph is increasing, not increasing, where the graph had a positive slope, where it had a negative slope, where it had a 0 slope. Remember those details? Well, when you have a positive slope, it actually comes about from the graph actually having an increasing value. Right? Think about what you know even just about lines back in, early middle school. If you have a line like this, the line's increasing, that means the slope's positive, right? And the same thing's true, but backwards if you have a negative slope. If you have a negative slope, then it means that the graph is decreasing. And if the slope is 0, well, you know you've got a horizontal tangent line at least, right? It may be a max, may not, maybe a min, it may not, but at least you know it's a horizontal tangent line. So I'm going to write that it may be a max or a min. It may not, but it could. Not max or max. Let's try that again. Max or min. All right, so let's take a look then at this particular graph. We are taking, not graph, but function. We're taking the function f of x equals x to the 4th plus 2x squared plus 1. And we're wanting to find out where the graph is increasing, decreasing, or neither. So neither might be a place where it has a horizontal tangent line. It also could be a place where it's just like flat, or maybe there's a jump in the graph or something like that. This doesn't have any jumps because it's a polynomial, but it could, in theory, have a jump in the graph. Well, we can actually decide where a graph is increasing, decreasing, or neither by finding out information about its derivative. So we're going to take a look about the derivative. So what is the derivative of this function? 4x cubed plus 4x, and that's it, right? So in particular, the easiest thing to figure out if something is increasing, decreasing, or neither is going to be looking at where the derivative is positive, negative, or 0. Okay? Now, back in algebra, when you looked for whether a graph was increasing or decreasing, or positive or negative, one of the common things that you did is you set something equal to 0, and you find the locations where it's 0 first. Finding 0 locations is usually the easiest option. So taking a look at this expression, 4x cubed plus 4x, how would I figure out where that is equal to 0? We can factor, right. So we can factor out of 4x, which would leave me with x squared plus 1. Is that right? Okay. And this is kind of like the ending result over here on this one right here. I've got to 4x cubed plus 12x equals 0, and I factored out, in this case actually it was a 4x as well. So I can factor out the 4x, and then what do? We set both parts equal to 0. So if 4x equals to 0, what does x equal? Yeah, x equals 0. How about the other one? Yeah, this one has no solution, right? 0 is a line through, it's not 0, it's no solution, okay? So this one has no solution because x squared is always positive, 1's always positive, you can't add two positives together and get 0, okay? All right, so we have just one location where it's actually going to have a slope of 0. So you've got one location where it has maybe a max or maybe a min, which means that on either side of it is probably going to be doing an increasing or decreasing kind of a motion. So imagine having sort of like a parabola, kind of a picture going on, something like that. All right, so what we can do is we could actually set up a number line, and we can test points. Now, our number line will have the point x equals 0 on my number line. And why x equals 0? Well, because that's the value that I just got when I solved this. So whatever value I get when I solve that, I can put on a number line. Everybody good so far? Okay, so I put the value, my x values, on my number line. And then what I want to do is I want to test points in the intervals. So I'm going to choose test points. You can pick any number you want in that area. So I need to pick a value that comes before 0 on my number line. And I can pick any number I'd like. So somebody give me one. Negative 1. That's a really nice choice because it's easy to work with. But if you wanted to pick negative 152, you could. Okay. You want to pick a test point on the right-hand side of 0 as well. 1's a nice one as well. Yeah. So these are the points we pick. Again, you can pick anything, so your answer is going to be the same in a moment no matter what you choose here. And then what we're going to do is we're going to test those points into the f prime of x equation. We're plugging them into f prime. Because f prime is going to tell us whether the graph will be positive for f prime or negative for f prime. And if I know the graph is positive for f prime, then I know the original graph is increasing. And if I know that the f prime is negative, then I know the original graph is decreasing. Are you guys following with me? So I'm testing using the derivative because it tells me information about the original graph. So what we're going to do is we're going to take f prime and we're going to plug in the two test values that we chose. So we're going to plug them into, maybe I'll put the graph or the equation itself in here just so you remember. We had f prime of x equals 4x cubed plus 4x. So when we plug in negative 1, it will be cubed times my 4, and then plus 4 times another negative 1. And I'm going to plug in the positive 1 cubed on that one, and so forth. All right, so what I need to know is I need to know what values I get in each of these cases. Negative 8, you said, Christian? Okay. And how about the second one? That one's positive 8. So what does that mean? Well, I got a negative here. So it means I have a negative slope. What does a negative slope look like? It goes down, right? It decreases. So visually, my graph is doing this. It's going downhill. Maybe not straight. I mean, obviously, I've got a polynomial, not a line, but it is going downhill. And then over here, I got a positive value. I don't really care that it's positive 8. I care that it's positive, though. Okay? And a positive graph, a positive derivative means the graph is doing what? Increasing. So my graph is doing this. And if I draw this picture, can you tell me what's happening at 0? What do we call that? A minimum. It's a minimum down there, right? Because I'm decreasing to a specific point and then I'm increasing afterwards. So I do have a minimum there as well. They didn't ask me that in this problem, but just recognizing that we can make that claim now as well. All right, so the question actually asks me to identify or determine where the function is increasing, decreasing, or neither. So my function is increasing from 0 to infinity, and it is decreasing from negative infinity to 0. It's going downhill from negative infinity to 0. It's going uphill from 0 to infinity. If you really want to put in the neither at the point 0, that's fine. It's not a big deal to put that in because we usually talk about an interval where something's happening, not a specific point. But if you put in neither at x equals 0, that wouldn't hurt anything. So, any questions on this? Okay, so let me just run through the details about how we make this decision again, because I know you have 4 problems to do and you won't see me inside class again to ask anything about how that worked or anything like that. But what we do is in order to decide where something's increasing or decreasing, we look at the derivative graph. So we take our derivative, we set it equal to 0, and we come up with these test points. We're going to call them critical points when we get to the next section, okay? The next chapter anyway. We're going to come up with these critical points, and these points are going to go on a number line. And once we have those points on a number line, we pick test points on any interval between between the critical points we have. So for instance, if I had 2 critical points, we'd have 3 test points, right? 1 in each interval. And then we test those test points inside of the derivative equation to find out if we get a positive, where our graph's increasing, a negative, where our graph's decreasing, or a 0, where we might have a max or a min. Yes, Emily?
How would you do it if your derivative didn't give you a solution?
If the derivative is not going to equal to 0, you mean? Then that means you only have one interval.
So it'd
It means you can test any point on the interval, and if it's positive, that means the graph's always increasing. If it's negative, it's always decreasing. Good question. Yeah. Yeah, it means you just have one interval. All right.